Hi there, and thank you for watching another video on electricity. I'm doing Ohm's law examples, and this is really quite a complex example. You'll see in a minute just why. Let's quickly go through it. Eventually they ask us to calculate the equivalence resistance. I'll explain that in just a minute, and also the resistance of R2. But what they give us is they give us the EMF of the battery, which is 23. What that simply means is that as the current passes through here, they leave with 23 joules per coulomb voltage, and they come back having no joules per coulomb. Okay, remember, a coulomb is a collective noun for a group of electrons, and so a group of electrons leave, they have this much energy, they spend all of the energy in here, so that the potential difference, the difference in the energy they had and they came back with was 23 joules and per coulomb, and that is that unit is voltage. Okay, so that's the one thing they give us. The next thing they tell us is that 2,343 amperes of current is flowing through R1. So in R1 we've got 2,343 amperes of current flowing into R1. Well, what does that mean? That means that every second, these coulombs with whatever much energy, every second 2,343 coulombs are entering into here and coming out. Now this is in a branch. You'll notice that if we follow the current, at this point some goes up and some goes down. So every second this many are passing through here. That means that every second more than this must be coming to the split, because only some of them are going through R1, the rest are going through R2. Okay, so that's what this means. Now when it comes to R1, and we'll look at that just now, they've also given us the size of resistor 1. So we know the current, and the size of resistor 1 is 4 ohm. Now this is enough to give me an idea of how much energy will R1 use. Let's do that immediately, and I'll tell you why, because they've given us enough information. Let's help the program out a little. Let's help the situation out a little bit by adding a bit more information. So I'm working with resistor 1, so I'm going to work with my ratio triangle and say, well, current in 1 is voltage over resistance. Okay, so I want voltage, so I'm going to say voltage. Now what is voltage? It is literally saying how much energy is R1 going to use. Okay, so when the coulombs get here, they've got 23 joules. They split up. Now, very interesting, in a parallel branch, each branch will use the same amount of energy. Okay, so no matter how much R1 uses, R2 will use the same amount of energy. That's great, because that gives me information not just about R1. If I can get the voltage of R1, I know the voltage of R2, because in parallel branches, each branch will use the same amount of energy. So velocity is I1 times R1. Velocity, I apologize, voltage. Okay, so the current in here is 2.343 times the resistance is 4. If you multiply that, you get 9,272, sorry. Okay, now why did I do that, or how is this going to help me? Well, here is a very, very important fact when it comes to parallel branching. If I do have a branch, and electrons split, it's called a parallel a branch, then the one thing that you have to remember is that the amount of energy that each coulomb will spend in the one branch will be equal to the energy he spends in the other branch. So even if there were 2 resistors or 10 resistors in this branch, he would spend the same amount of energy in the whole branch than he would in the whole of the other branch. So the amount of energy spent here Remember what voltage is? Voltage is joules per coulomb. So every coulomb will spend 9.372 joules on this resistor. So I'll put a little voltmeter reading here, a voltmeter here, and say that when the coulombs come just before the resistor, they'll have 23 joules each coulomb. Remember, we don't divide this into parts because this is every coulomb, and even though not every coulomb goes here, every coulomb has 23 joules. So 1 coulomb comes here and he's got 23 joules, but he spends 9.372 on this resistor. So after he spent that, how many joules does he have left? Okay, so in other words, when the coulomb comes here, he has, let's write it there, 23 minus 9.73 is 13 13.628 volts. That's how much energy they have when they come here. So 13.628. Now when the coulomb comes here, as he's traveling along, all of the coulombs must have the same amount of energy, which means when the coulombs that go up here will also spend in this whole branch 9.372 joules of energy. So in the end, if I put a voltmeter reading here, it will also have a potential difference of 9.372 volts. Excellent. That's why I did it. Now that means if I were to take the difference in voltage between this point and that point, if I were to take the voltage here, now again, what do I do when I take the voltage? I take the difference between each the energy of each coulomb, and then, well, they started with 23. Both of the branches, each coulomb spent 9.372, which means if I measure the voltage, the energy per coulomb now, I will also get at this point that they have 13.628. So the difference, remember, voltage is measures the difference in that is 9.372 voltage. Okay, now again, if I were to take the voltage between this point here, okay, so when the coulombs come here, they haven't spent any energy. Now they split up again and they spend energy in this branch and in that branch. So when they come here, they've spent all of their energy. By this point, they've got 0 joules per coulomb. And so if I take the voltage over these 2 points, I know that they started with the energy they had left at this point, and that was the energy they had left, and they spent all of the energy. So this voltage reading here must equal 13.628. Can you see how just getting the voltage reading here gave me so much more information about this whole complex system? It's a very complex system. Okay, and now we can add in the rest of the information, and that is 5 and 5. So here we've got 5 ohm and 5 ohm. Okay, so I know it's not always wise to just go and put in as much information as you can before you've actually read the question, but since I do know what the first question is, I know it takes a little bit more information. They ask us to calculate the equivalent resistance. Now, equivalent resistance just refers to the resistance, the total resistance in the whole system. Now, total resistance you can do in a number of ways. You can either just add up all the resistors, but because we have parallel branches, it might be a little bit more difficult. So for example, my total resistance, I would take as the resistance of branch 1. I'll take the equivalent resistance of this branch, not branch 1, parallel grouping. That you see there's a parallel grouping here, and there's a parallel grouping there. So let me change that from branches to parallel grouping 1 plus the resistance of parallel grouping 2. And to find the resistance in parallel grouping 1, I'll have to take, because they are parallel, there's 2 parallel branches, I will take 1 over the resistance in branch 1 plus 1 over the resistance in branch 2. Okay, and we'll see that branch 1 would be this one and branch 2 would be that one, and so we would just be able to enter those values. The problem is we only have resistor 1. Resistor 2 we don't have, and in order to calculate resistor 2, I would have to use my diagram, and that would be voltage over current. So resistor 2 would equal voltage 2 over current 2. And here you'll see, great, we have voltage 2. We actually added it onto our sketch by the effort I did on voltage here. But unfortunately, the current in 2 we don't have. Yes, we have the current that's going through resistor 1, and if we had the total current, we could subtract it, because we know if we had the total current, it splits, so we get some and the top branch gets the rest, but we don't know what that one is, so we don't have I2. Okay, so I2 we could go calculate, since we need the total resistance. We could go and say, okay, well, I can get the total current is equal to I1 plus I2. In other words, I could use the fact that in this current it splits, and so in other words, this is really a long route around, but I don't have total current. I've got the current in 1, but I don't have this one. So let's circle the ones we don't have. Okay, so now I see, okay, I don't have total. Now I can go and get total. And this monotonous color is frustrating me, but let's keep it pink then. I can get total current by saying, okay, total current is equal to total volts divided by total resistance. And then, unfortunately, I do not have total resistance. This is what I'm trying to calculate in the beginning. So I see I actually have a circular route. Okay, so that doesn't help. But what I could do is say, okay, wait a minute. I have total current at this point as well. So in other words, when the current is going in to branching, the parallel branching 2, or the parallel grouping 2, that is still the total current, because even though it splits at this point, it comes together again at that point. So I've got my total current. Let's highlight where the total current is. There's the total current. The total current is comes out here, then it splits. Okay, so now these two branches aren't total currents anymore, but then they come together again. So I've got total current again here, and then it splits again. So as it splits, then it comes back together here again. Okay, so notice that this voltage reading here is the voltage reading over total currents. Okay, and it's the voltage reading over the parallel grouping 2, and in parallel grouping 2 I have both of the resistors, which which is great. So I might not have the total resistance, but I also know that the total current flows into parallel grouping 2. So if I take the voltage over parallel grouping 2, and I take the resistance of parallel grouping 2, I can get the total current as well. And so I'm definitely going to do that, because the total current in this question will be very, very helpful, I promise you. So let's work out the total current. The total current is equal then to the total voltage over grouping 2, which we've already calculated, is 13.67, was it? 13.62. 628 divided, now we just need the total resistance of these two branches. And now to get the resistance in there, I'll take resistance of the parallel group 2 is equal, and because it's parallel, I must do this, I must take the 1 over. So 1 over resistor 3 plus 1 over resistor 4. So resistor 4. Both of them is 1 over 5 plus 1 over 5, which means 1 over RP2 is equal to 2 over 5, and then RP2 is therefore, now I flip them around, 5 over 2. So let's actually write it as 2.5 ohm. So the individual resistors have an ohm of, or resistance of 5 ohm. The equivalent resistance, in other words, if I were to imagine the whole thing as one thing, this whole grouping is one resistor, that resistor would represent a 2.5 resistance ohm. Okay, and it kind of makes sense, because remember, resistance is obstruction to flow. So when the coulombs come to this point, if they only had to go to through one resistor, they would have a 5 ohm resistance. But now they've got two options. I don't just have to go in one path. There's two paths I can choose, making the resistance effectively halving the resistance. It's not always the case that it's exactly half, but it is always the case that it's half when the two resistors are equal in size. Okay, so we'll put that in here, 2.5 ohm. And now I'm going to use my calculator for this calculation, and I get 13.628 divided by 2.5 gives me a total current of, what was that, 5,4512 amperes. This is great. This really is great, because look at this. We now have total voltage and we've got total current, which means I can get equivalent resistance. I don't even have to do this whole process anymore, which is absolutely excellent. I am supposed to calculate total resistance. Total resistance will be total voltage divided by total current. Total voltage we know is 23 divided by total current, which is 5.4512. Excellent. So I'm going to just store this value, memory store, and then I say 23 divided by memory recall, and that gives me total resistance is 4,21925. Let's round. I'm going to store this value as well, but I'm going to round it to 4.22. 4.22 ohm. Okay, now what this means is that if I had to consider this whole thing as a unit, So I can just answer there, 4.22 ohm. If I had to replace all of the resistors and all of the branches with a single resistor, it would look like a simple diagram like this. There's my battery. Okay, it's the wrong way around than there. Okay, but that's not a big problem. And this whole thing can be replaced with a simple diagram with a 4.22. That's why we say equivalent. Equivalent resistance is as if I'm taking all of it and replacing it with a single resistor, and that resistor will have 4.22 ohm. Now, what it also means is that if this whole unit together is 2.5, then these two together must be the opposite of, must be what's left. So this branching, I would take 4.22 minus that, and it will give me that resistance there. And I say that because in the next question they tell us calculate the resistance R2. Now you can do it in that fashion, but let's look at R2. R2 just by itself I could calculate by taking the voltage over 2 divided by the current that goes into resistor 2. Now we already have the voltage. See again how helpful it was to calculate this voltage over 1, and because the amount of energy we spend in this branch is equal to the amount of energy we spent in that branch, we have the voltage there, but we don't have the current. But getting the current I2 is very easy now, because we have the current I1 and we know that the current split up. We got the total current, we just calculated it in the previous question. There's the total current, and so all we can do now is take that 5.45, so this 5.4512 gets split up. 2.343 goes into branch 1 and the rest goes into branch 2. So of 5.4512, 5.4512, subtract from that this branch 2.343, and I get an answer of 3.1082. 3.1082. That is the number of coulombs that come into this branch every second. Now again, if this number goes into that branch every second, all of these come to this point and all of these come to that point, so when they reach this point they come there at the same time again, which means here we go again, the full current is at this point again. But that's not as important, I just wanted to stress that fact again. But into R2 every second we'll have 3.1082 coulombs per second. So here the voltage, each one of those coulombs spends 9.372 volts or joules. In there goes 3.1082. There we go, that's correct. So let's do the calculation. So it's 9.372 divided by 3.1082 gives me 3.015. 3.015 ohm. Okay, so you could have rounded it. Well, this is already rounded lower to 2 decimal places. 3.02. Now this is probably, if we look at these values, they're all whole numbers, so it's probably supposed to be 3 ohms, just because in the process we have rounded off quite a few times and used rounded values obviously a small error is coming in. We've rounded about 4 times already, so a small error has come in. So this is probably 3 ohms, but I think that answer would be acceptable. So thank you very much for watching. I hope that you've had an instructive lesson, and that this complicated thing has really been simplified just by understanding what is voltage, what is current, and analyzing the picture best you can. Thank you for watching. We'll see you in the next video.